Hi everyone, my name is Mayra Melgoza and I am a postdoctoral in the CIO, which is an optical center in León, Guanajuato, Mexico. And today I'll be talking about some of my research work using the trivalent European ion as a spectroscopic proof, employing as a lanthanide ion in the synthesis of 3 European metal organic frameworks. Here we use 3 different ligands. Here there are we have their chemical structures. We can abbreviate it like BTC, TTC, and BTC. We can observe in the first and second, we have 2 carboxylic groups where European ions can bond, and these ligands are called B-dented ligand. For this one, we have 3 carboxylic groups where the European ions can be bonded, and they are called a tridented ligand. Another difference we say about the ligand is this one, BTC and BTC have a benzene ring, while for TTC we have a aromatic ring of 5 with a sulfur atom in the ring. So then first, the European MOFs were fabricated by isothermal method using DMF and water as solvents. And in the water was added the surfactant CETAF, and the precursors are dissolved, and the mixture is heated at 120 centigrades degrees for 24 hours. Then the precipitation is cooled down and the material is washed with ethanol and is left drying and heating at 80 centigrades degrees for another 24 hours. Then we have more final material, the European MOFs. So the synthesized European MOFs present crystalline structures confirmed by powder X-ray diffraction, and we also can see the crystals morphologies obtained by cell micrographs. We observe that the morphology depends with the ligand used in the synthesis, and for the 3 systems, the crystal size is even up to 100 micrometer long. The crystals obtained were huge. So we also can see that by the choice of the organic ligand, the luminescence properties can be modified and affected the JUDD-OFELT parameters. The JUDD-OFELT parameters were calculated using the emission spectra, and how we can calculate it are upload the image with the equations. So the analyzing these intensity parameters can give us information about the environment surrounding around the European 3+ ions. So here in the first table, we observe the values, the JUDD-OFELT parameters values calculated for each system. We observe that for this system, EU-BTC and EU-BTC, the parameter of omega-2 is higher than omega-4. So first to continue, the omega-2 is calculated using the intensity of hypersensitive transitions, which is this one, 7F2, and is present in is the most intense in the three systems. And omega-4 is calculated using the intensity of this transition, which is also electric dipole transitions, but it's not hypersensitive transition. And it's the 7F4. So as said before, these two have a trend where omega-2 is higher than omega-4. So which means that omega-2 have a high values. This could indicate that the europium and the oxygen in the ligand are bonded covalently, and also will indicate a high intensity of these transitions could indicate that the europium ion is in a sites with asymmetry. A high asymmetry environment. So for this one, we can observe a inverse trend where omega-4 is higher than omega-2. The omega-4 is related with the rigidity of the medium where the europium ion is embedded. So as the literature say that this ligand TTC is a rigid ligand, while these two have a little flexibility. So this indicate this is according with the literature say. So also we present some image proving the Eu-MOFs as sensors. The Eu-MOFs were proved with some solvents and were observed some quenching in the luminescent intensity for the some of the solvents. We are still working in these proofs, so that's all we have until now.